Hey, AP Physics 1 students, this is Mr. Heinrich, and I'm here to help you out with your progress checks from AP Classroom. So it's very likely that in the next few months, as you're studying for your AP Physics 1 test, that your teachers will release these questions to you, and they're not easy. They are like FRQs, free response questions. So over the next few months, I'm going to go through every unit in the curriculum, and I'm going to unpack every one of these progress checks. So tonight, recording right now, is going to be Unit 1, Problem 1, which is a projectile motion question. And while I'm transitioning over there, please like, please subscribe, and please ring the bell because, like I said, you're going to get notifications when the next progress check is ready to go. So here comes the first one. We got a dart that's being fired off horizontally, and it's coming from some height h, it's going a distance d, and it's going to hit its target over here. Now, the fact that it's being thrown completely in the horizontal direction at the beginning is a huge help. That's always my favorite type of projectile motion problem because they are more manageable. So what do they want from us? The dart lands on its target at time t1. They want us to sketch what's happening with the velocity in both the y and the x-axis as a function of time. Now, if you look at the dart in any one of these intermediate positions, or even right here, you know that it's at a diagonal. So that diagonal velocity it has is made up of both x velocity and y velocity simultaneously. So looking at their graphs, they want us to sketch them out. We don't need to provide actual values, we just need to show the rough sketch. So what I would realize right away is that at the beginning, there is only x velocity, there is no y velocity. So let me get over to my dot cam and show you what I mean. Okay, so we've got quickly a dart that is being tossed and it goes down and hits a target. Again, it's coming from a height of h and being or landing on the ground at a distance d at its target. So initially, as I already stated, it's all velocity in the x-axis. Now that little zero there, that means initial right there. Some teachers use an I use a little zero for V naught or V initial x. And it has some value, and V initial y should also be stated. It is 0 meters per second. There is no y velocity at the very beginning. It's purely in the x-axis. Now, in the very next moment, there's absolutely some y velocity. Look what I just did there, right? I made my y velocity appear and my x velocity stay exactly the same. Why is the x velocity the same at every single moment in the fall? Well, because there's no acceleration in the x-axis. If there was, I would start flying towards the wall right now, even as I sit here. You would as well. There is no acceleration in the x-axis. Therefore, whatever velocity we give that dart remains the x velocity the entire trip. However, because we have a negative 9.8 meters per second every second in the y-axis, we can expect that speed up that I was talking about. And so I'm just going to kind of show that, even over exaggerate the fact that my velocity is kicking up by how much every second? Every second it's kicking up by 9.8 meters per second in the negative direction. So getting to the question A1, how does that play out on this graph? Well, if this is Vy, and this is some time called T1, at the very beginning, there is no y velocity, therefore we should say we're at the origin. By the way, these are the positive values and these are the negative values of velocity. And we're not even going to be in this region because all of our y velocities are negative, right? So in the first moment of time, we gain some negative velocity. And in the next moment of time, we gain some more negative velocity. But notice that for every unit of time, the amount of y velocity I gain is the same amount because we're dealing with a constant acceleration. For every moment of time that passes, in this case, a second, we are speeding up by a steady amount every second. We're speeding up by 9.8 meters per second every second. All right. So that is why you see this linear graph. It's a consistent negative speed up. And that's it. That's what you do for that one. And the other graph is plotting Vx versus time all the way to T1. Okay, well, it was already stated I could go to any one of these velocities, this Vx or this Vx, and guess what? They are all equal. And I might add they're all to the right, which by convention is positive, right? Right is positive. So that means I'm not going to be in this negative section at all, right? I'm going to be in the positive section of my x velocities. And you can just choose some value that's positive up here and just hold that thing steady all the way to T1. And that's it. You're done with A1. I hope that made sense. Let's go on to A2. Now, A2, without going back to the handout right now, it says a lot of stuff, but it asks you to, in terms of H, D, and physical constants like G, right? Gravitational acceleration. They want you to find the launch velocity. That's what they're asking for. So I will go over there so you can read it for yourself. All right, so what does it say? It says the height of the platform is then increased, but the target is not moved. Oh, too far. That is B. Starting with a kinematic relationship, derive an expression for the launch velocity needed for the dart to hit the center of the target. Express your answer in terms of H, D, and physical constants as appropriate. So that's what I was saying. Okay. Now, 9 times out of 10, I'm telling you, 9 times out of 10, you will go straight to this kinematic equation. And when I say this kinematic equation, I mean for both the x-axis and the y-axis. Because remember, with projectile motion, even though the time is the same for both the x and y axes, what's happening in the x-axis is pretty different from what's happening in the y-axis, which is why we need to analyze the math in the x and the y separately, knowing that our go-between is that time. The time is the same for both axes. All right, let's get into it. Let's look back at our model here. Well, that's great information. V naught y is 0. That means I get to call this 0, and this entire expression drops out because 0 times t would be 0. There's definitely a y, that's acceleration in the y-axis, and that would be negative 9.8. But let's talk about the x-axis. Is there any acceleration in the x-axis at all? Nothing. So that would be 0. And 0 times a half times t squared, all of that stuff is 0. So let's expand this. Remember what delta means. It means a final position minus an initial position in this case, because it's delta x, right? Delta v would be final velocity minus initial velocity. Delta anything is a final minus an initial, equals v naught x t. And counterpoint, let's go down to our y. I'd say y minus y naught is equal to 1/2 ay t squared. Now, these look like they're straight from a textbook, and we're dealing with terms that aren't necessarily these terms. So let's use these terms now and input them into these two different expressions. Well, what is x? X is the final x position, which happens to be what? D. And what's the initial x position? 0, right? So I know we call this whole distance d, but if we're looking at them as positions, if I go all the way from 0 all the way over to here, I would call that a position d. So I'd say d minus 0 equals, what about v naught x? What in the world is that? Well, that was your initial velocity. Isn't that the same thing as your initial launch velocity? So this problem is referring to V naught x as VL. That is your initial launch velocity. And it purely is in the x-axis, as I already stated. So for V naught x, I'll put in VL times t. And I'll clean it up a little bit and rewrite it as D equals VLT. Now, this is very important as we look at progress checks throughout the rest of this curriculum. This is not done. I could solve this for VL. Undoubtedly, I could do that. But while D is a given that I know, T is not. T is not one of the terms that I'm allowed to express the answer in. So I am going to come back to this equation, but not yet. Let's come down here to the y equation, find an expression for t in terms of that stuff, and bring it back into this equation. Okay, so what's your final height? The dart starts up here and then boom, hits the ground. So if it ends up on the ground, isn't your final height 0? And what is your initial height? Well, your initial height is h. So I'm going to write, don't forget there is a minus sign there. You can't get rid of that. There's a minus h now, equals 1/2. What is ay? Well, ay, we already said, is g. Now here's where we have to be a little bit astute, right? If I just put a g and then I put a t squared, I'm going to have a negative here, which I can't have because I'm about to take the square root. And you can't have a negative in a square root. Well, if I was just solving this like a problem in a book, I would solve this whole thing, and at the very end, I would plug in negative 9.8. So can't we agree that G actually does have a negative value when we plug it in, right? So I'm going to put a negative in front of it just like that, and realize that these negatives cancel out, which is great. And I'm going to get H equals 1/2 GT squared. Let's now solve this for T. So to do that, I would multiply both sides by 2 to get rid of the half, and I would divide by g. And you would end up with t squared equals 2 times h over g. And finally, we take the square root of both sides, boom, boom, and you get, give me a second to move my paper. You would get t equals the square root of 2h over g. And we're so close. Let's finish up. I'll box that as well. I'm coming back to this equation. There it is. And I'm going to say, you know what? Let's solve it for VL. Wouldn't you agree that to solve for VL, you would divide both sides by t, right? So I'd have VL equals d over t. D over, hello, that's what t is, the square root of 2h over g. And that would be your answer. Now, I would accept that, but you always want to make it look as pretty as possible, right? Let's put a little bow on top. You could multiply top and bottom by root g, so to speak, and then kind of put everything under the root again so that you would have that. Does that make sense? You could multiply top and bottom by root g, it would cross out this root g, and you'd have root g up here over root 2h, and d would be on the outside. And you would just pull all of that stuff under the root like I just did. And there is your answer to A2. And it's really important that you see why is the answer? Why is it the answer? Because my answer for VL is in terms of D, G, and H. And then, of course, 2 is just a constant. So that's why it's right. Okay, let's go to the last part, and we are done. In this part, we don't even need to use pencil and paper. We could, but that would take longer. There is a mathematical way to prove part B, but let's just talk about it. It says the height of the platform is then increased, but the target is not moved. Indicate whether the launch velocity should be increased, decreased, or should remain constant for the dart to still hit the center of the target. Justify your claim. So remember, they want you to make a claim. When you're doing these kinds of short responses, they want a claim. Here's your claim. I'm just looking at it again. Okay. I would say the dart needs to be launched at a slower speed. Okay, that's what you got to say. The dart needs to be launched at a lower velocity. That's your claim. Now let's prove it real fast. If the height is increased, as suggested, then it will have more hang time. If it has more hang time, it would go further at the same velocity. Therefore, the velocity must be reduced in order for the dart to go the same distance d. Did you get all that? I'll say it one more time. Make your claim. The velocity of the dart must be decreased. If the height is increased, the dart would have more hang time. And if it maintained the initial velocity it had, it would go too far. Therefore, the velocity must be reduced so that it travels the same distance d. Anyway, you can take either one of my explanations and write your own or write one of those. And I hope that helped you. Again, I'm going to be doing these progress checks a lot. Like, subscribe, ring the bell, and I'll talk to you on the next one. Have a good day.